Today I want to talk about the another topic not in the high energy physics. In the solid state physics, they also used some spontaneous symmetry breaking, so-called SSB. Originally, such a symmetry breaking mechanism is mostly adopted in the uh, solid physics topics like the superconductivity, and this is applied to the Higgs mechanism of particle physics with the same idea. So still we talk about the how the superconductivity can be explained by the symmetry breaking in the 2 point of view, both through the microscopic view with the BCS theory, and the second, we talk about the macroscopic view with the Landau-Ginzburg's theory. So first of all, the superconductors is a solid which has a no resistance for the current. This is discovered by the owners by using the wicked helium with the low temperature with 4.2 Kelvin. This is called the traditional superconductor. And in 1986, the new types of the superconductors that are with the relatively large temperatures, uh, which is the critical temperatures given by the 92 Kelvin. This is called the high TC superconductor. So the below the such critical temperature TCs, the largest terms become the Joule in the such superconductivity. Um, so now let's talk about the microscopic point of view with the BCS theory. The in the BCS theory, the electrons and electron pairs, which is called the Cooper pairs, uh, formed by the electron-phonon interaction. Uh, by the Coulomb terms, originally the electrons has repulsive forces, but with the phonon interactions, they have the attractive forces. So the such interaction terms is given by the following potential from the Coulomb constant, and the other terms are given by the wave factors of the electron and the electron's energy and the phonon frequency. This is a similar form to the propagators in the high energy physics. And when the Cooper pairs are formed by the electron-electron pair, and there will be the lattice. The solid lattice will be vibrated, so that it makes a phonon as a virtual particle, and they interact each other. And the Cooper pairs forms a boson, and the many Cooper pairs can exist in the ground state, so that it makes the no resistance. And such a Cooper pair state can be described by the following wave functions as the quantum mechanics regime. Uh, we can define the relative distance and the center of the mass. And this can be expressed by the momentum space by the Fourier transformation. So here's the K mode and K mode white, and the K mode is given by the plane wave form. And this Cooper pair state satisfies the following Schrödinger equation. There will be the attractive interaction term and the binding energy is in the right hand side. And the solution of this equational motions satisfy the following relation K mod white and the attractive interactions potential. And that K mod white is given by the following form. First of all, the summation of the momentum space has a cutoff with the divide frequency omega d, which is the possible maximum frequency through the lattice. And there will be the attractive interaction terms will be obvious. And K mod white has such a form. As a propagator form, the binding energy minus and the energy term. And so there are two inequalities in here. First of all, the summations of the K momentums has upper bound related with the device frequency and the Fermi energy, and also the two electron which forms the Cooper pair should have the slightly have a deviations from the Fermi C. So by using the two kinds of inequality, we can find the energy gap for the Cooper pair. So that this is the momentum space. So there will be the upper bound of the epsilon k energy associated with momentum k, and there will be the lower bound, the electrons momentums allowance from the Fermi C with a small deviation. And we can know that there is a energy gap for the Cooper pair. And we can describe the BCS theory by using the Beard quantizations, like as a quantum field theory. We can define the bosonic creations and annihilations of light from the electrons fields of light. The momentum and the spins are emphasized in here, and the Cooper pair creation and annihilation of light B and the B daggers can be defined. They satisfy the bosonic commutator relations so that they can be occupied ground state with many degree of freedom, so they make the no resistance. And by using this B and the B dagger, we can construct the Hamiltonian for the BCS theory. The Boss sum is given by the energy. This is the same with the typical harmonic oscillator, and there will be the interaction term because this is not free theory. The interaction between the Cooper pair term. And we can obtain the BCS ground state from this Hamiltonian. First of all, there will be the coefficient, which is given by the probability for the creations of the Cooper pair, so that we can ask the Cooper pair creation applied over the vacuum. Then we can obtain the ground states of the such a BCS Hamiltonian. And by using that, we can calculate the Gibbs energy in the statistical formalism by the expectation value of the such a Gibbs energy over the ground state. Then we can calculate so on, and that minimizing sort of this gap Gibbs energy, we can define the energy gaps in here as the from the Cooper pair interaction. So the such a Cooper pair interaction potentials given by the such attractive interaction term when the Cooper pairs exist such a inequalized interval. So by using that we can calculate the energy gap as a self-consistent integration. This is just the calculation process, and you can find the detailed calculation process in some quantum field theory or the statistical physics, like as Arthur-Croput or the gifted amateurs for the QFT. And for the zero temperatures, the energy gap can be evaluated by such integration. And such energy gap in the zero temperatures will consist by such a term. So this is our result of style. This is consisted by the divide frequency of the phonon in the lattice and the density of the state for the electron at the Fermi C level and attractive interaction term. And in the finite temperatures, when the energy gap is equal to Joules, that temperature is defined by the critical temperature. So the critical temperatures can be considered by the similar form. Here is we assume the magnetic field is zero. So the typical scale of the divide frequency is a electron volt, and the attractive interaction and the density of state is the order of the 0.1. So the critical temperature is given by the 30 Kelvin, which is expected value of the typical superconductor. So So far we consider the microscopic theory of the superconductor. Now we talk about the macroscopic, some phenomenological presume and effective theory, which is called the Ginzburg-Landau theory. This is already many discussed in the statistical physics thermodynamics. We can define all the parameters as the wave function, which is the basis above the critical temperature Tc. Then it means that the above the critical temperatures, the Cooper pair number density becomes zero, so there will be no superconductivity. And this is something varied when the such a wave functions changes slow over the spatial, so almost constant, homogeneously in the spatial point of view. And under the field assumptions, the brief energy is given by such a form. This is the well-known form. So there is the quadratic term and the quadratic term. And the quadratic terms depends on the temperatures. So when the temperatures are below the critical temperatures, the quadratic term becomes a negative. This gives the Mexican head potential. So the other parameters, the psi, becomes the non-zero as the minimum sort of the display energy. So the symmetry is spontaneously broken. Here's a U1 symmetry is broken, which is associated by such a wave function. This can be the transformed with the U1 factor, but above the critical temperatures, the quadratic term becomes a positive, so the other parameters becomes used to make the minimize sort of the free energy. Here's the there of the U1 symmetry sort of the wave function with the phase factor. So there will be no Cooper pairs for the high temperatures, so the superconductivity will be lost. And if we add the magnetic field term, there will be the additional term, and this can be described by the London equations with some electric or magnetic fields. So we can combine such a microscopic and the macroscopic point of view. First of all, there will be the energy gap in the BCS theory. And we can construct the Hamiltonian, and we can calculate sort of the partition functions. And in the statistical mechanics, the free energy can be obtained by the ln of the partition function z, and this can be expanded about the wave functions, and the free energy has such a Landau-Ginzburg theory form. So now we discussed the superconductivity with the spontaneous symmetry breaking with the 2 point of view, the Boston and the BCS theory with the Cooper pair and the equation of the motions, and how the energy gap and the critical temperature is determined in the microscopic view. And the second we discussed the Landau-Ginzburg theory with the free energy as assumption that the effective theory.